These are my physics corrections. My name is Sahana Manoharan. So this first problem I got wrong. The correct answer was actually the graph that went negative and then positive. You can see in my notes that force is the negative derivative of potential energy. And since the potential energy graph has alternating positive and negative slopes, the force graph must alternate between positive and negative values. The force graph transitions from negative to positive as predicted by the potential energy graph. This next question, the correct answer was actually 20 joules. The graph shows a potential energy peak at x equals 0 with U equaling 20 joules. For the particle to travel from very far to the right to very far left, it must overcome its peak. If the particle successfully crosses x equals 0, it will convert its potential energy and reach far to the left. Question 5, I got wrong. It's just kilogram meters per second. Watts is a unit of measure. I don't know why I got that wrong. Number 6, I took the ratio of the final initial powers, but used the net force as the final thrust force. What I should have done was use the net force to solve for the final thrust force. You can see in my notes an equation that I probably could have used, but I did not. So the correct answer is actually 0.11 and not 0.6, or 6 as I put. Question 9. The correct answer was actually U equals 1/4 kx to the 4th. You can see in my notes some of the formulas I could have used, and then solving it out. The correct answer choice comes from letting integration constant equal 0, and I did not do that, so that's why I got that wrong. So number 10 I got wrong. The correct answer was actually, since the component of gravity is always directed towards the original position of the block, gravity is a conservative force. And there's several conservative forces. I listed them out in my notes. And since the normal force is always perpendicular to motion, the normal force is a conservative force. And my wrong answer was, mistaking that. So number 11, I got wrong. The answer was actually 32 newtons in the negative x direction. And you can see in my notes I wrote some rules about that, and the force on a particle is the negative derivative of the potential energy, and then below it is some calculations that would have helped me solve the problem. Number 14 was actually 6 mg watts, and in my notes you can see some energy formulas, and the velocity at time equals 3 seconds could have been solved using the conservation of energy, and there's a bunch of calculations under there, which is what I should have done to get the right answer. So you can plug in the values they give you and find instantaneous power. The answer to number 20 was 1/2 mv squared plus mgd sine theta, and I didn't account for internal energy. So the work dissipated is the change in mechanical energy. The initial energy is 1/2 mv squared, and the change in gravitational potential energy is mgd sine theta. The total energy dissipated is the sum of these two quantities. So the correct answer to 22 was the work done by the spring on the cart is directly proportional to the initial kinetic energy of the cart when it reaches the spring. Using the work energy principle, the initial kinetic energy of the cart is converted into the potential energy stored in the spring, and the work done by the spring can be calculated by the force applied over the distance compressed. By measuring the force exerted by the spring and the distance it compresses, the work done by the spring can be directly compared to the initial kinetic energy of the cart, showing the relationship between them, and you can look at my notes for some related information. The correct answer to 23 was 1/2 Ka squared. The total mechanical energy in a mass spring system without considering dampening is 1/2 Ka squared, and then the dampening force affects the energy dissipation over time but does not change the initial total mechanical energy. And then I have notes about work energy theorem to back this up as well. The answer to 125 was 160, and work is the change in kinetic energy, and I've did a bunch of calculations based on that. And in my notes, you can see that I wrote down that work is the transfer of energy in and out of systems. So knowing that information, you could solve for 160. Number 26, the correct answer was L/4. The velocity has a constant acceleration. For the velocity to be half as much, the distance traveled has to be 1/4 as much. The correct answer to 27 was m1 over m2 minus m1 times k. The forward momentum of the projectile equals the backward recoil momentum of the gun. You'd have to square both sides and multiply by 1/2, and then separate out one factor of mass to get the gun kinetic energy and projectile energy for k, and then you'd solve for k to get the correct answer to this problem. The answer to 29 was m over big M minus little m times v initial. If the nucleus is initially at rest, the total momentum is 0. The total final momentum is also 0, and the nucleus has a new mass of big M minus little m. It lost mass m to the ejected particle. The correct answer to 31 was 3 meters. On a frictionless incline, an object's acceleration is constant. With constant acceleration, x infinity t squared is 2 seconds. The object travels 4 times farther than in 1 second, therefore the object is 4 meters down the incline. Since the object is 1 meter down the incline at 1 second, the object travels 3 meters between the first and second seconds. Number 32 is pretty self-explanatory when you realize that work is the integral of force with respect to distance, and then solve from there. Correct answer to 35 was x max equals 0.2 meters and v max equals 1.4 meters per second. The solution correctly calculates the speed, but uses the amplitude, or what I did was use the amplitude of potential energy to graph the maximum displacement of the block's motion, and instead I should have substituted it into the equation u equals 1/2 kx squared and then solved from there. So the correct answer here was, does the cord obey Hooke's law? And I've listed some conservative forces in my notes. The cord obeys Hooke's law if a force versus stretch graph is a line, which the graph is not, which answers this question. And since we cannot tell if the cord transfers energy from potential to thermal or anything else, we also cannot tell the breaking strength of the cord, the force that will snap the cord from this graph. And the last question I got wrong was 37. The correct answer to this was actually the car is moving uphill while the driver operates the gas pedal. If the car's mechanical energy, kinetic energy, is decreasing, but the car Earth system's mechanical energy, kinetic plus potential, is increasing, it means that the increase in potential energy due to the car moving up the hill is greater than the decrease in the kinetic energy. The car must be moving uphill, and the gas pedal is being operated to convert chemical energy into mechanical energy, increasing the car Earth system to total mechanical energy. And those are my corrections. Thank you.